Hello, morning. So this session, I think it's session 10th. I'm going to talk about Möbius transformations. In fact, we defined yesterday what is a Möbius transformation, but we continue with the properties of such maps. Recall in the last session we introduced Möbius transformation trying to study the set of holomorphic automorphisms of the Riemann sphere. Riemann sphere, the complex plane plus the point at infinity. So we showed that a biholomorphic map between C bar and itself, it's always something like a map like this. Where A, B, C, and D are arbitrary complex numbers, with the only condition that such that the determinant of the matrix of the four coefficients is not zero, in order to that coefficients not cancel, and numerator and denominator doesn't cancel, don't cancel. Okay. These maps are called Möbius transformation. Let us observe that we are studying also the point at infinity. So with this expression, for instance, the image of the point at infinity would be a limit of this expression with z tend to infinity. So is the point A over C. Okay, and the image also of a point minus d over c, I think, must be the point at infinity, because it makes zero the denominator, so it must be infinity. So with these conventions, we have defined a map, a bijection between C bar and itself. And the result we had stated yesterday was the following: that the following three categories of maps generate every Möbius transformation, that are: one, translations, maps like this. Second, we have homothesis. Here A is a complex number, here B is different from zero. And third, the inversion. I called J yesterday, 1 over Z. So with these three maps, you can generate any Möbius transformation. How can you do that? Take any Möbius transformation, T, for instance. Assume first that the image of infinity is the point infinity. This means that C is zero, in fact. Okay? Yes. This means that C is zero. So in fact, such a transformation, if taking infinity to infinity, must be written like this: AZ plus B. So in the denominator we only have a constant, so we can write like this. Okay, and this can be written as A times Z plus B by A, and this is a composition of a translation with a map with a homothesis here. So we are done. In this case, we are done. And if not, if T is any map, let's say T sends, let's say, infinity, some point Z0 to infinity, okay, we could consider in this case the map, for instance, G of Z is 1 over T of no, it's not that. Now we are going to consider the map F, no, G of Z, sorry, no, it's not this map, sorry, I made a mistake. The map F of 1 over Z plus Z0, okay. And this map takes infinity to infinity. Infinity here goes to 0, here goes to Z0, and goes to infinity. So this map takes infinity to infinity, so this map can be written as the composition of a translation and an homotopy, and this map also, this is F, sorry, it's not F, it's T here, okay? This map is T, is composed to this map that is, first of all, we make an inversion, and after we make a translation. So it's something like, first of all, we make the inversion, and after we make the translation of point Z0. So G can be written like this, and we can, from here, we can see that T is again, as G is a composition of a couple of Möbius transformation, a couple of those simple Möbius transformation, T is also the composition using this way of writing. Okay, so in fact, any Möbius transformation is composed of, in fact, at most 4 of these transformations here. Okay, G is the inversion here. Inversion here. Okay. In fact, this is composed by G is composed by 2 Möbius transformation, and so T is composed by at most 4 Möbius transformation. In fact, okay, from this expression. Okay, this is one of the properties of the Möbius transformation we stated yesterday without, but we didn't have time enough to prove. Second property interesting to show is what is called transitivity, or first of all, perhaps we will speak about fixed points of a Möbius transformation. Fixed points. So we are going to study the set of points that are taken into themselves by a Möbius transformation, where T of Z is Z plus B. Okay? So again, consider 2 cases. First of all, assume that T of infinity goes to infinity. So infinity is already a fixed point. Assume that infinity is already a fixed point. So in this case, T of Z is AZ plus B. So it may have another fixed point or not. If we equal this to Z, we have 2 cases. If A is equal to 1, well, of course, assume that T is not the identity map. If it's the identity map, everything is trivial here. So assume T is not the identity map. If A is equal to 1, as T is not the identity map, B is not 1. So Z plus B equal, B is not 0. So Z plus B equal to Z means that, well, this is impossible. No more fixed points. Okay? And if A is different from 1, there is another fixed point. So another fixed point would be the point something like minus B divided by A minus 1, something like this. Okay, another fixed point. Okay, so we have at most 2 fixed points in this case, infinity and perhaps another fixed point here. And if in the general case, if T of infinity is different from infinity, so in the general case, we can consider this expression here. So if C is different from 0, you can consider this expression equal to Z. So we have the square plus the dz equal to AZ plus B here. So C Z square plus D minus AZ minus B equals 0. C is different from 0, so you have order 2 polynomial that has, of course, two roots, at most two different roots. So there is at most 2 fixed points again. Okay, there are most 2 fixed points, and there is a case when there is only 1 fixed point. 1 fixed point means that the discriminant of this polynomial is 0. This means that D minus A square plus 4BC is 0. This is the condition in order to have only one fixed point. This condition usually is written differently. Let us consider the matrix here. Let us consider the matrix of the Möbius transformation here. So this condition, we are going to write it differently. Instead of writing like this, we are going to write d plus a square minus 4ad plus 4bc equal to 0. Why? D plus A is the trace of this matrix. So this is the, let's call M of T, this matrix. So this is the trace of M square minus 4 times AD minus BC is the determinant. So this condition means that only one fixed point appears. Let us observe that in the preceding case, where T of infinity is infinity, in this case, the matrix was something like this, B 0, 1, AB 0, 1 in this case, and the condition for having only one fixed point was A equal to 1. A equal to 1, if we look to this expression, the trace in this case is A plus 1 square minus 4 determinant for A. And I guess this is 0 if A is equal to 1. Because this is A square plus 2A plus 1 minus 4A. There is, okay, so something, A square, there is something that, is it correct, these computations. A equal to 1 is the condition in order to have only one fixed point, so the trace A plus 1 to the square minus 4 times the determinant. Okay, this is correct. A square plus 2A plus 1 minus 4A. So this, yes, this is A minus 1 to the square equal to 0. Okay, it was correct. I thought that I had made a mistake. A minus 1 to the square equal to 0, so A equal to 1. So, any case, this is the condition. This is the condition always to have only one fixed point. If this condition is not fulfilled, if this number is different from 0, there are two fixed points. Sometimes, as I also said yesterday, a Möbius transformation has different matrices, so you can multiply or divide by anything, okay, by any constant, any different from 0. So to have another expression, another different matrix. Sometimes we use what we call a kind of normalized expression for the Möbius transformation. It's the following: if you consider this matrix, the determinant of this matrix is lambda square times the determinant A, B, C, D. So the determinant of the original matrix. So we can always find lambda such that this is equal to 1. For instance, we can take 1 of the determinant, you take the square root, so you can always use a kind of normalized matrix assuming that the determinant D minus BC is equal to 1. In this case, we have very few flexibility. The only thing we can change is that perhaps we can change the signs here. So this would be the same, A, B, C, D would represent the same Möbius transformation with this condition, A, D minus B, C equal to 1, such that minus A, minus B, minus C, minus D is the only flexibility we have now, okay? So sometimes we use this condition. If we have this normalized expression, the condition for, in order to have only one fixed point would be that the trace is plus or minus 2. Using, if the determinant is 1, the trace might be 1 or minus 2 in order to have only one fixed point, okay? If not, we have two fixed points. Okay. So a Möbius transformation, in fact, we have has always either one or two fixed points. In particular, it has always at least one fixed point. Okay, but this is also a topological fact. Perhaps if you have studied enough topology, you may know perhaps that if you have any map, any topological map from the sphere S2 to itself, it has any continuous map, it has always at least one fixed point. This is a topological fact, in fact. But we don't, this is a hard theorem, quite complicated, but here is, of course, it's much easy. Okay, so we have at least one fixed point. So, in particular, you know that if you have a Möbius transformation with three fixed points, and this fact will be used sometimes, if you have a Möbius transformation with three fixed points, it is the identity map, always. Because if it's not identity, it has only one or two fixed points. Okay? Second, another property is what is called three transitivity. Three transitivity means the following. Consider 3 points, these three different points on C bar. Okay? There exists exactly one Möbius transformation such that T of Z1 is 0, T of Z2 is 1, and T of Z3 is infinity. So we can take any 3 points by a unique Möbius transformation to 0, 1, and infinity respectively. How can we do that? Okay, well, this is quite easy. If you want to take Z1 to 0, you need to have some Z minus Z1 somewhere, okay, in the numerator. If you want to take Z3 to infinity, you are going to divide. And now, if you want to take Z2 to 1, okay, the value of Z2 here is Z2 minus Z1, Z2 minus Z3, so you can divide this by this number. This is a constant here. So this Möbius transformation verifies the statement. Okay, so there is at least one Möbius transformation that verifies that. And why is it unique? Is it unique? By the previous consideration. If you have two such Möbius transformation, T1, T2, now you may consider, for instance, T1, T2 minus 1. This is a Möbius transformation that takes that Z1, Z2, and Z3 into themselves. So it has 3 fixed points, so it is the identity map. It is the identity map, so we are done. T1 is equal to T2. So this property is normally called three transitivity. Any 3 points can be taken into Z1 and into 0, 1, and infinity. And in fact, more generally, any 3 points can be taken into any 3 points. So, in fact, you can generalize a little bit that statement there, and to show that if you take any 3 points, any 2 couples of 3 points, Z1, Z2, Z3, take any 3 different points in C bar, and another set of 3 points, there exists exactly one Möbius transformation T taking Zi into Zi prime. And the argument is the same as before, or we can do the following. We can take, for instance, T1, a Möbius transformation taking Z1, Z2, Z3 into 0, 1, infinity, constructed as before, and T2, another one taking Z1 prime constructed as before, and well, now you only need to consider this composition that takes your points, your Z points into your Z prime points. And of course, the same argument as before shows that it is unique. Okay, so any 3 points can be taken into any 3 points, which is another relevant property of Möbius transformation. Okay. The next one, the next property what I would like to mention is property related with circles. I'm going to define a circle, because a circle here is not going to be exactly what you are thinking. So it's not going to be exactly something round like this. Traditional circle, but a little bit more general. Remember the stereographic projection we had yesterday? Yesterday we defined the stereographic projection between the sphere. Okay, we project it into the complex plane here. Okay, the North Pole. Okay, now imagine you take a circle, okay, traditional circle, let's say, on the sphere, and you project this circle into the complex plane. This is going to be called a circle in the complex plane. What is a circle in a sphere? A circle in a sphere is always the intersection of the two spheres with a plane. So take a plane that cuts the sphere. So take a plane, in general, alpha x1 equal to delta. Okay? Take a plane like this, and you are going to project this circle called C, this circle. So this is, this is a plane that cuts the sphere, for instance, in a circle here. And you want to project this circle into the plane. So this called pi the stereographic projection. So a point Z is in the projection. This is the same of saying that pi minus 1 of Z must belong to this circle. And remember that the expression, we have expression, analytic expression for the map pi minus 1. Pi minus 1 of Z was something like 1 over Z squared, modulo of Z squared plus 1 to x. X was the real part of Z, to y, and Z squared minus 1 was the expression of the inverse of the stereographic projection. So we need that this point is on the circle. So we need that alpha 2 alpha x Z squared plus 1 plus 2 beta y Z squared plus 1 plus gamma Z squared minus 1 Z squared plus 1 equals to delta. Points that are on the projection verify this equation, and working a little bit, we obtain the following equation. So, okay, this is 2 alpha x plus 2 beta y plus gamma Z squared minus 1 okay, and this can be written like this: gamma minus delta Z squared, okay, plus 2 alpha x plus 2 beta y plus a certain number that must be minus gamma minus delta, okay? It's correct. Something like this. Okay. So this is a general equation that we will be calling a circle. So this is normally a circle, a traditional circle, but it can be another thing. For instance, it may happen that gamma equals to delta. If gamma is equal to delta, this term does not appear. So what you have here is the equation of a straight line. When can that happen? When can gamma equal to delta? Gamma is equal to delta only when the point 0, 0, 1 belongs to the original circle, so the north pole. Of course, if you take a plane passing through the north pole, it cuts your sphere in a circle that goes through the north pole, and the projection of this circle is a straight line, because you are in the same. You are projecting. In fact, you are cutting a plane with with a complex plane. So in this case, you have a straight line, and in fact, any straight line in C, any real straight line, can be is the projection of some circle. If you take any straight line here, you can take the plane that contains this straight line at the North Pole. You take that plane. This plane cuts your sphere in a circle, and the projection of this circle is exactly that straight line. Okay? But if not, you have a traditional circle. But any of these two objects, either straight lines or circles, circumferences, will be called a circle on C bar. Okay? So this will be called a circle. A circle. This equation, normally we are going to write it a little differently. This number, call it A, for instance, A square. We are going to define the number omega, define the complex number omega as, let me see, alpha plus I beta. So in this case, this number here is 2 times the real part of Z times omega bar. Okay, Z is X plus I Y. If you multiply by alpha plus alpha minus I beta is the omega bar, you obtain, you multiply by 2, you obtain this number. So minus C equal to 0. Where omega is some number, some complex number. Or alternatively, you can write this plus Z omega bar plus Z bar omega minus C equal to minus C or plus C, sorry, plus C. I'm going to write plus C here, sorry. I always forget the signs here. Okay, you take some numbers. So this is a general equation of a circle here. A general equation of a circle. You can verify from this equation that for instance, if A is equal to 0, okay, it's perfect, it's a straight line. If A is not equal to 0, this corresponds exactly to the following circle. If A is not equal to 0, this equation here corresponds to X plus alpha divided by A to the square plus Y plus beta divided by A to the square equal to gamma plus delta A plus alpha square in the original equation, beta square A square. It corresponds to this circle. And this expression here, with the new notation, we have gamma plus delta is minus C. So we have here minus C divided by A plus, this is omega square divided by A square. This must be greater than 0. If it's not greater than 0, we don't have anything here. So this means, in fact, that we must have this condition. So one such equation is really a circle. So if it can be written like this with A and C. Recall, there are real numbers, A and C real numbers. Omega is any complex number. Verifying this condition that omega, the modulo of omega square, is greater than AC. In fact, you can see this is a geometrical condition because this means exactly this condition that the plane you have taken cuts the sphere. In principle, I took any plane here, any plane in anywhere in R3 may cut the sphere or not. So if the distance of this plane to the center of the sphere, to the origin, is greater than 1, it doesn't cut the sphere. So the condition for this plane to cut effectively the sphere is exactly this one, this condition. Okay? And it's the same for a straight line. If you have a straight line, I mean if A is equal to 0, so if you don't have this term here, if A is equal to 0, the condition here would be only that omega is different from 0. Omega different from 0 means that, in fact, this expression we have a straight line. If this term does not appear, this term represents a straight line if this appears. If not, we only have a constant here, constant equal to 0. So this appears effectively, if this is not 0, only if omega is not the 0 complex number. Okay, so this is the condition to have a circle. So we have defined circles over the Riemann sphere. A circle may be a circle, a circumference, let's say, or a straight line. Okay. Let us observe that with this notation, the center of the circle is the point minus alpha over A minus beta over A. So the center with the point minus omega over A, where omega is this complex number, and the radius would be something, the radius to the square would be something as omega square minus A times C divided by A square would be the radius. If A is different from 0, so you have effectively traditional, let's say, traditional circle. Okay, with this equation. So why circles are important? Well, one interesting property of Möbius transformations is that a Möbius transformation takes always circles into circles. A Möbius transformation takes circles into circles. T takes circles into circles. Now it's quite easy to show it. Any Möbius transformation is composed by translations, let's say, homothesis, and inversion. A translation, of course, takes straight lines into straight lines and circles into circles, no problem. Okay? And homothesis is the same. So there are affine transformations, so take straight lines into straight lines and circles into circles. And what happens with inversion? Consider the equation. Consider a circle, a general circle having this equation. With the condition omega square greater than AC. Okay? And take the inversion. The inversion was the map. Z goes to 1 over Z. So, if you take the inversion here, you obtain this equation plus you obtain this equation, you remove the denominators, so you have here C Z square plus omega Z plus omega bar Z bar plus A equal to 0. Remember that in this equality related with complex numbers. Okay, and this is again the equation of a circle. We only have changed omega by omega bar, by the conjugate of omega, and the condition is still fulfilled, because the condition now is omega bar squared, but it's the same as omega bar, greater than, instead of having A times C, we have C times A. Of course, the condition is still fulfilled, so the inversion transforms any circle into a circle again. Okay?
What is the circle passing through the origin?
It is transformed, a circle passing through the origin is transformed in a straight line. So, yes, that's why it's interesting to consider both at the same time, circles and straight lines. So the condition would be like this. If, let's say, if one of the, you have a circle, for instance, if one of the points of the circle, you have a Möbius transformation such that some of these points goes to infinity, the image is a straight line. And if not, the image is a circle again. Okay? And if you have a straight line, more or less the same. If some point of the straight line goes to infinity, the image is again straight. But if any point of the straight line goes to infinity, the image would be a circle, like this. Okay? So, yes, you can play with straight lines and circles, and let's say traditional circles. Okay? You can play with these two kind of objects. Okay, and there is another way of showing this, that is through a concept associated to, that is sometimes useful to, I'm not going to use it too much, I think I will not use it through these lectures, but sometimes a concept associated with Möbius transformation that is sometimes useful is the concept of cross ratio. Cross ratio, that is the following one. Well, in fact, it's a concept that comes from projective geometry. Some of you have already studied some projective geometry. You have learned about cross ratio. One way of defining cross ratio is the following. Consider 4 different points on the Riemann sphere C. Consider 4 different points. And take there is only one Möbius transformation T, you know, that takes respectively the points Z2, Z3, Z4, respectively into 0, 1, and infinity. There is only one Möbius transformation that performs this, that converts this point into these points. And now take the number T of Z1. T of Z1, that is a point, or perhaps it's not infinity, okay? In this case, it's not infinity, but take this number, and so this number is going to be called the cross ratio of Z1, Z2, Z3, and Z4, and sometimes is represented like this. There are some alternative definitions, sometimes, well, reverse in order, or of course using projections, as is used in projective geometry, etc. But one possible definition is this one. Okay, this number is called cross ratio, and in fact it can be computed as the following: Z1 minus Z2, Z3 minus Z4, Z1 minus Z4, and Z3 minus Z2. Well, if some of the points is infinity, you must arrange things conveniently to have this definition, to eliminate some terms, something like this, okay? But in general, you have this expression for the cross ratio. And a property of the cross ratio is that if you have, imagine you have another Möbius transformation S, any Möbius transformation S, so Möbius transformation preserves cross ratio. So the the cross ratio of 4 points, the cross ratio of 4 points is exactly the cross ratio of SZ1, SZ2, SZ3, SZ4. And this is quite easy to show. This is quite easy to show. Why? If you want to compute with this definition this cross ratio of these points, you need to find a Möbius transformation that transforms these 3 points into 0, 1, and infinity. And which is the good Möbius transformation? You can take h minus 1 times t, composed by t. This transformation takes s of z2 into, first of all, into z2, and after that into 0, etc. So this is the good one. So now you have to evaluate this map in S of Z1. So you obtain the same cross ratio. So Möbius transformation preserve cross ratio. Okay? And it can be shown that, well, it's not difficult to show, but for instance, 4 points, any 4 points, lie on a circle, 4 points lie on a circle. I'm not going to show that. Well, we could show after the previous results, we could show easily, but 4 points lie on a circle if and only if its cross ratio is a real number, or perhaps infinity, using that definition. It's if and only if condition. For instance, it is very easy to see if you have, your circle is, for instance, the real straight line. In this case, is obvious. Assuming that you know that you can, that any circles goes into circles by Möbius transformation. If you have any circle, you can transform it always into the straight line by a Möbius transformation. You take any 3 points on the circle. You take the only Möbius transformation that takes these 3 points into some real points. You choose 3 real points, any real points. One of them, for instance, you take the infinity, and the 2 other to take 2 real points. So there exists one Möbius transformation that takes these 3 points into these 3 points. So this Möbius transformation must necessarily take the circle into the real line. Okay? As for the real line, this is obvious, and Möbius transformation preserve cross ratio. You know now that the original points you had on the circle necessarily must have a real cross ratio. This is one way to show it using the previous results. But you could show it also in a geometrical way. This can be shown also in geometrical way, and use that, for instance, in order to show that Möbius transformation transforms circles into circles. If you know that this is true, and it can be shown also without using previous results, so in a completely geometrical way, if you know this is true, okay, you take 4 points that are in a circle, for instance, and you know the images must be, the cross ratio of the images must be real, so the 4 points must be also on a circle. So this means that the circle is transforming into a circle. So different ways of proving, different, let's say, orders of proving of the results. Okay? But what is important is, of course, the result and another notion, and I think the last notion I would like to introduce is the notion of, for the elementary properties of Möbius transformation, is the notion of symmetry. Symmetry. For straight lines, it's quite well known what means symmetry. For instance, if you have the real line, you take a point here, Z, and the symmetric would be a point here that would be the conjugate of this number. Okay? if you have, for instance, some transformation that takes this straight line into itself, perhaps moving the points, a translation like this, or something like this, it takes symmetric point into symmetric points also. Okay? For any other straight line, it's also quite clear what it means by symmetric. It would be the point, some point here. But what does it mean for a circle? If you take a circle, a traditional circle, let's say with center P and radius R, there is a well-known geometric transformation called inversion with respect to a circle. Inversion with respect to a circle that is defined as follows. This is quite geometrical. Take a point Q here, any point, for instance here on the circle, or on the inside, or in the exterior, it's the same. And we're going to find in this same half line another point here Q prime. Take another point here Q prime such that the product of Q minus P of the distance Q from the first point to the center times Q prime minus P is the square of the radius. There is only one point that verifies this condition. This point, in fact, must be the following point. It must be the point P plus R squared using complex coordinates divided by conjugate of Q minus conjugate of P. You can verify easily, it's a very easy computation, so that the point Q prime is this point. Q prime is called the inverse of P of Q with respect to the circle C. Okay? And this is going to be the equivalent of the symmetry. The equivalent of the symmetry. Because it can be shown that, in fact, if you call symmetric 2 points that are, if it's with respect to straight lines, the usual notion of symmetric. If it is with respect to a circumference, to a circle, you call these points one inverse to the other, you call them symmetric. It can be shown that symmetric points are always taken into symmetric points. I mean, if you have a circle C, if you have a Möbius transformation T, okay, such that this Möbius transformation transforms the circle C into another circle C prime. Takes circles into circles, so it transforms like this. You have 2 points here, Z1, Z2, symmetric with respect to C. Symmetric with respect to, to C. Then T of Z1, T of Z2 are symmetric with respect to C prime, always. Again, there are many ways of showing that. You could show directly using, for instance, the expression of the symmetry. If you take, for instance, a circle of equation as before, A z squared plus omega z bar plus omega bar z plus c equal to 0. Okay, you can construct precisely the expression of the inversion, and you can verify that this is a little bit long, but it can be verified. But I think to finish, I'm going to give a very short and geometric argument to show that is the following. How can you characterize points that are symmetric with respect to a straight line? If you take any straight line, in a straight line, 2 points are symmetric with respect to a straight line if and only if the following condition is satisfied. If you take any circle through these 2 points, either a straight line or a circumference here, any circle, this circle cuts your straight line orthogonally. And the symmetric points with respect to straight lines verify these properties. It is an if and only if. In fact, the straight line through these points must be orthogonal, is orthogonal also, of course, and any circle that passes through these 2 points is orthogonal to your straight line. And the same happens with inversion. If you take the inversion, if you take 2 points that are inverse one to the other, if you take any, this can be characterized by the fact that if you take any circle passing through these 2 points, these 2 circles are cutted orthogonally. For instance, this has something to do with a property that is called the power of a point with respect to a circle. A power of, it was very useful in old books or classical geometry. If you take any circumference, any circle here, if you take a point, the power of the point with respect to a circle can be defined like this. You take any straight line that cuts your circle in 2 points, and you take the product of this distance times this distance. This is independent of the straight line you have taken. In fact, this is this distance to the square. So using this notion, okay, this times this is this distance times this is r squared. So the power of the center of your circle with respect to this circle passing through Q and Q prime is r squared. R squared, that are the square of the radius of the original circumference, and r squared is also this square. So this point must be here, this point must be orthogonal. It's more or less that the reason. And so inverse points are also characterized like this, and it's a fact that in fact I haven't proved it, but I mentioned that any Möbius transformation, for instance, conserves always the angles. In fact, any conformal mapping, any holomorphic mapping in points where the derivative is not 0 conserves the angles. So if you take 2 lines, two curves, you take the images, the angles are the same. So it conserves orthogonality. Using these facts, and using that circles go into circles by Möbius transformation, you can show that inverse symmetric point must go into symmetric points, because this is a geometrical property that is preserved by Möbius transformations. Well, it's a quite beautiful, perhaps, way of proving this property. Okay, using some geometric consideration, but it can be proven in many different ways. What is interesting is that inverse are always taken into inverses. So I finish here. This is more or less a list of the main properties of Möbius transformation. Thank you.